Hello, everyone. Thank you for listening to my talk today. So in 1992, a best-selling book was written by John Gray, American author and relationship counselor. The main idea behind this book was that the most common relationship problems between men and women were the result of innate psychological differences between the sexes. To describe this, he used a metaphor. Men are from Mars and women are from Venus, in which he stated that men and women come from different planets, and that we are acclimated to our own planet's society and customs, but not to those of the other planet. Now, one of the topics discussed as to why men and women come from different planets is the idea that we respond to stressful stimuli differently. A very simple example of this would be when stressed, maybe women want to talk about our feelings, whereas men may want to be left alone. But as a neuroscientist, one of the first questions that pops into my head is why? What is the biological basis for these differences in behavior? And this brings me to what I want to talk to you about today. It's the idea that from a fundamental biological perspective, men and women really are different. Or to use the metaphor, men really are from Mars and women really are from Venus. And yet we know so very little about biological sex differences in behavior, health, and disease. And this begs the answer to another two questions. Why do we know so little? And does it even really matter? So to begin to answer these questions, I want to talk a little bit about neuropsychiatric disorders, something I know a little bit about. Now, the connection may not be immediately clear, but please bear with me for a moment. So in neuropsychiatry, for most of these disorders, we haven't exactly done the best job at finding novel, therapeutic, efficacious drugs. Oh, sure, over the past couple decades, we've actually done okay in improving the side effect profile of these drugs. But in the grand scheme of things, they actually don't work much better in improving symptoms. Let's take depression, for example. Depression is a heterogeneous disorder that can be very difficult to treat. We have drugs that work some of the time. They have side effects, some worse than others, and they can take a very long time to work in those that do respond. And in those that don't, it can often take many trials with many different drugs before we find one that works, if we even find one that works. And let's not forget that relapse is always a serious concern in depression. Clearly, in this case, a one-drug-fits-all strategy does not work. Now, in our defense, as a preclinical researcher, we try. We really, really try. We are passionate about what we do. We come to work every day, and with the help of amazing staff and fabulous trainees, we run our experiments looking for mechanisms of disease, the identification of novel therapeutic targets, and we test the safety and efficacy of novel compounds. We're doing everything right. But are we really? Did you know that women live longer than men, but also suffer from more chronic illnesses, delayed diagnoses, misdiagnoses, and also suffer from more drug side effects than men do? Let's go back to our example of depression. Women are twice as likely to develop depression, and they also suffer from heightened stress susceptibility, which is a major risk factor for depression. There's even evidence to suggest that men and women respond to antidepressants differently. So again, I have to ask the question, what's the biological basis for these differences? Well, unfortunately, I can't give you that answer. And the reason that I can't give you that answer is because we simply don't know. And one of the main reasons that we don't know is because historically, preclinical research, which studies mechanisms of disease, have predominantly used male subjects. And this male-centric research is by no means restricted to depression. Now, this was a study that examined 10 biological disciplines. And what they were looking for was how much of this research included males, females, or both. What they found was in 8 out of the 10 disciplines, there was a significant male bias. Disciplines that included physiology, pharmacology, endocrinology, behavior. Neuroscience was actually one of the worst culprits, with 5 studies done in males for every 1 that was done in females. Now, when we look at the data as a whole, we can see that almost 50% of studies only used males in their research. 19% didn't even disclose what sex was being used. 25% actually did use both males and females, and they should be applauded. But of these, the majority did not even examine sex as an experimental variable. So this study is from 2018. Let's fast forward to 2020, see if we're doing any better. So this study did the same thing, where they looked at inclusivity of males and females in research, but they focused on neuroscience studies, both preclinical and clinical. So when we look at the preclinical studies in the rats and mice, we're not doing any better. About 75% of these studies used either only males, or they used both sexes but did not examine sex as a significant experimental variable. Now, the clinical studies did a little better in that they were more likely to include both men and women in their research. But again, same problem. They did not look at sex as an important biological variable. So if there are important sex differences in behavior, health, and disease, how are we going to know what they are if we never actually study it? So this appears to be where we're at, with the big iceberg representing what we know about men in health research, disease, and behavior, and the small iceberg representing what we know about women. So how did we get to this place? How is it that we have focused all our attention on the males? Well, there have been a few assumptions that have been made over the years that have led us here. The first assumption is that when we look at our experimental data, females are more variable than males. And this is owed to hormonal variation across the estrous cycle. And this jumps right into the second assumption, that if we use females in our research, they have to be staged, which means that for every parameter that we look at, we need to know what stage in the estrous cycle these animals are in. Now, I'm not up here arguing that female hormones don't have biological effects. Of course they have biological effects. But guess what? Male hormones have biological effects too. And as it turns out, recent studies have shown that in fact there is little to no differences in variability between males and unstaged females. And I'm just going to give you one example here. So again, we're looking at neuroscience studies, and here they examined differences in experimental data variability between males and unstaged females across various methodological approaches. And as you can see clearly, there was variability in the females. And it is likely that female hormones actually contributed to this variability. But males also showed variability. Why are we so much less concerned about what contributes to this variability? And this leads us to the last assumption. Now, when we incorporate females into our research, of course, we have to increase the number of animals that are used. This does lead to increased costs. But it is assumed that it also delays progress. But if there are important biological sex differences, isn't it important that we know what they are? And if we knew this, wouldn't this, in fact, increase progress? So I'm up here talking to you about inclusivity in preclinical research. And yes, I might talk a good talk, but I also walk the walk. And I want to show you some of my own research, which will help reinforce why we need to use both sexes. Now, one of the things that I work on is brainwaves. This is electrical activity in the brain that is critical to communication both between brain regions and within brain regions. Importantly, these brainwave patterns are highly coupled to behavioral states and disease states. And in my research, I look at sex differences in these brainwave patterns in the context of neuropsychiatric disorders. Now, brain waves are made up from various frequencies as shown. And in our research, we look at sex-dependent effects of stress on these brainwave patterns and the relationship to the development of depression-like behaviors. Now, when we take rats and we expose them to very mild stressors over the course of a long period of time, they develop these depression-like behaviors. But what we notice is that some animals are susceptible to the stress insofar as they develop these behaviors much sooner. We call these rats stress susceptible, and they are different from those animals that develop the depression-like behaviors later, which we call stress resilient. So one of the parameters that we can look at when examining these brainwave patterns is something that we call spectral power. And to put it very simply, spectral power is related to the amplitude of the wave. Now, when we looked at female animals that were exposed to these stressors, we saw that those that were stress susceptible actually showed a decrease in theta power and an increase in delta power across a number of regions in the brain. We did not see this in the females that were stress resilient. When we looked at the male animals, the first thing we noticed is that they took twice as long to develop these depression-like behaviors. So they were already showing a resilience to the stress that the females did not have. However, when we compared the susceptible and the resilient males, we found no stress-dependent changes in these brainwave patterns that could distinguish between these two groups. So another parameter that we could look at is something called coherence. And again, in very simple terms, this is related to how well two brain waves synchronize. When we looked at the females, we saw a widespread decrease in theta coherence across multiple brain regions in the stress-susceptible animals only. We did not see this in the stress-susceptible males. In fact, when we looked at the stress-susceptible males, we found no brainwave signatures that we could use to actually identify them. What we did see was a change in the resilient males when they were exposed to stress. And this was a widespread increase in gamma coherence. So what does this tell us? It tells us that even though males and females may have behaviors that look the same, the underlying mechanisms that regulate these behaviors is in fact different. And it gets better. We actually went back in time because we wanted to see how these brainwave patterns changed upon initial exposure to stress. We found that these changes occurred relatively early, and in fact, we could use them to predict with high accuracy which animals were going to develop the depression-like behaviors sooner or later. So we could identify the stress-resilient and stress-susceptible animals in a sex-dependent way before these behaviors developed. And what's even more remarkable, when we looked at the females, and the females only, they showed very unique signatures that we could use to identify those animals that were stress susceptible or stress resilient before they were even exposed to the stress. We were very excited about this because we thought not only can we use sex-dependent brainwave signatures as biomarkers for established depression, but maybe we can also use them to identify those that have increased depression vulnerability. And this could lead to increased monitoring and early interventions as necessary. So this brings me to the end of the talk. And if there's one thing I hope that you get from this is that inclusivity is very important. And although I've spoken about it in the context of preclinical research, it really is important in everything we do. When we are inclusive, we enrich the lives of everybody. Thank you.